Hi everybody, it's Professor Mitchell. We're continuing with Chapter 2 today on polynomial and rational functions. And today we're going to be talking about Section 2.3, which is polynomial functions and their graphs. The objectives of this section, you can see them here. We're going to identify polynomial functions, recognize characteristics of graphs of polynomial functions, determine end behavior, use factoring to find zeros of polynomial functions, identify zeros and their multiplicities, use the intermediate value theorem, which you'll hear a lot more about in calculus, understand the relationship between degree and turning points, and finally we'll put all that together to graph polynomial functions. All right, so don't be scared by what you see here. This is just yet another example of something looking more complicated than it really is just because of notation. So the definition of a polynomial function is if you let n be a non-negative integer and let all of these numbers a sub n minus 1, blah, 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 all the way down to a sub 0, be real numbers. So remember, that means they could be fractions, decimals, whatever, with a sub n not equal to 0. Then the function defined like this, f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1, blah, 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 plus a2 x squared plus a1x plus a0 is called a polynomial function of degree n. The number a sub n, which is the coefficient of the variable to the highest power, is called the leading coefficient. So I want to convince you that this is a lot simpler than it looks by just showing you a couple of examples. So all this is really saying is that we are adding together a bunch of powers of x with some numbers attached to them. So one example of a polynomial function would be something like 2x to the 5th minus 3x to the 4th plus 7x squared minus 6. Or g of x, it's not that easy for me to type a fraction here, but here we'll do it like this. Negative 1/2 x to the 6th plus 0.7, that kind of makes me twitch a little bit, mixing fractions and decimals. So you see it's just powers of x added together with numbers attached to them. All right, very, very simple. What's not so simple is finding my mouse once I've been typing. So give me a second here. Now, give me a second. Where is it? Okay, I'm getting warmer, I think. I was thinking about pausing the video while I do this, but I'm almost there. There it is. Okay. All right. Yeah, I was trying to make my text box bigger so that this one here wouldn't wrap around, but hopefully you get the idea. All right, so continuing. Graphs of polynomial functions are smooth and continuous. Polynomial functions of degree 2 or higher. And I'm not really I don't really understand why they're limiting it to 2 or higher. I think degree 1 are smooth and continuous, and so are degree 0 even. But anyway, by smooth, we mean that the graphs contain only rounded curves with no sharp corners, so nothing like an absolute value. And by continuous, we mean that the graphs have no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. Continuity is a huge, huge concept in calculus. And we'll define it in a different way in calculus. But this is the super unofficial definition. You can draw the graph without picking up your pencil. All right, end behavior. So the way that I like to explain end behavior, The behavior of the graph of a function to the far left or far right is called its end behavior. Although the graph of a polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound as it moves far to the left or far to the right. So in other words, a polynomial function can't just go like this forever and ever and ever and ever like a trig function does. The sign of the leading coefficient, it turns out, and the degree of the polynomial function reveal its end behavior. So here's how I like to explain this. Picture the graphs of x squared. Sorry, I've got a box in my way here. I'm going to try to move. There we go. Picture the graphs of y equals x squared, y equals negative x squared, y equals x cubed, and y equals negative x cubed. So after doing chapter 1, specifically, I want to say section 1.6, you should be able to picture these graphs pretty quickly. These were, or at least y equals x squared and y equals x cubed were part of our library of common functions. And then, of course, by sticking a negative sign in front, what does that do? Flips the graph upside down, right? So picture these graphs. Are you picturing them? Hopefully you have a picture in your head that looks something like this for y equals x squared and y equals negative x squared. There's y equals x cubed. I got these from a bunch of different places on Google Images. And there's y equals negative x cubed. I'm sorry that these two sort of seem to have a different shape. I got them from 2 different places, so they're just drawn on a different scale. But technically this should just be this flipped over, right, about the x-axis. It's a vertical reflection. All right, so the reason I'm having you picture these is because these actually illustrate your 4 different kinds of end behavior. Y equals x squared is a polynomial of degree 2, and the important thing about 2 is that it's even. And furthermore, its leading coefficient is 1, and the important thing about that is that it's positive. All right, you want to say odd, but actually the determining things are, number 1 is the degree even or odd, and number 2 is the leading coefficient positive or negative. So any polynomial, it turns out, with even degree and positive leading coefficient has this kind of end behavior, both ends pointing up, going towards positive infinity. And I mean, if you were ever doing this for me on paper, it's perfectly okay to just draw 2 arrows pointing up if I ask you about end behavior. Even degree and negative leading coefficient, like this, is both ends pointing down. I have to keep my fingers in front of my face because my virtual background, see, kind of makes weird things happen. Maybe not. Sometimes my hand will disappear. All right, and then these 2 have odd degree. If the leading coefficient is positive, now I have to be really careful because the image that I'm looking at of myself is mirrored. So I'm pretty sure that to give you the correct end behavior for odd degree, positive leading coefficient, even though this looks backwards to me, I think it will be correct for you. And then if the degree is odd and the leading coefficient's negative, both ends just flip, okay? So it's pretty easy to make a little table for that. In fact, that might be worth doing on the tablet. I didn't think of that. So give me just a second here to get this going. Okay. Let's close this. Let's get rid of this. And let's start a new one. Uh-oh. I don't know if you can see that. It's asking me to do something with iTunes. I don't really want to do that right now. Okay. So let's see. I want to do a new share. Okay. Here we go. So summary of end behavior. 4 different kinds of end behavior for polynomials, depending first on whether the degree is even or odd, and then depending on whether the leading coefficient is positive or negative. So top left corner is like y equals x squared. So that's both ends pointing up. Bottom left corner is like y equals negative x squared. So that's both ends pointing down. Top right corner is like y equals x cubed. That's down to the left and up to the right. Bottom right is like y equals negative x cubed. That's left end going up, right end going down. All right, those are your 4 different kinds of end behavior for polynomials. Okay, so I don't expect I will be using the tablet again today, but you never know, so I'm going to keep it on. Okay. All right, so we have the leading coefficient test, which says that as x increases or decreases without bound, the graph of a polynomial function eventually rises or falls and does not go like this. All right. Here's a more complicated version of the thing that I just scribbled for you. I think I like my version better. It's a little simpler, so I'm not going to hang around this slide very long. It says exactly the same thing I just showed you on the tablet. All right, so using the leading coefficient test, we're going to use the leading coefficient test to determine the end behavior of the graph of f of x equals x to the 4th minus 4x squared. So number 1 is the degree even or odd. It's even, right? This 4 right here makes it even. Is the leading coefficient positive or negative? It's positive. It's a 1, this invisible 1 here. So even degree, positive leading coefficient. That's just like y equals x squared. That's both ends pointing up. All right, or the way they say it in words is the graph rises to the left and to the right. And I've even thrown in the graph of this function here for you. So later on, we're going to talk about how to draw graphs like this. Notice that this function is even, all right? It has y-axis symmetry. Now, I don't want you to think that every even degree polynomial is an even function, all right? Because that's not true. Maybe think about why that's not true. Can you come up with an example of an even degree polynomial that is not an even function? All right, let's talk about zeros. If f is a polynomial function, then the values of x for which f of x is equal to 0 are called the zeros of f. So it's kind of a funny term. It's saying any number that makes the function equal 0 is called a 0. These values of x are called the roots or solutions of the polynomial equation f of x equals 0. So the word zeros does not mean exactly the same thing as roots or solutions, but it's pretty close. I actually didn't understand the difference until maybe, might have been 10 years ago. Functions have zeros. Equations have roots or solutions. Roots and solutions are the same thing. Each real root of the polynomial equation appears as an x-intercept of the graph of the polynomial function. So there's another related concept. X-intercepts of the graph. They come from zeros. All right, so in this example, we're going to find all zeros of the function f of x equals x cubed plus 2x squared minus 4x minus 8. And the way that we're going to do that is we're going to set this function equal to 0 and solve the resulting equation. Okay, so all this stuff came up at once. I would have liked for it to come up one line at a time, but I couldn't make that happen. So let's just take it line by line. And you read this going down this way, and then you jump over here. Okay, so here's the function. I set the function equal to 0. So now I am going to factor this polynomial. And the way that you usually factor a 4-term polynomial is by grouping. So I'm going to look at the first 2 terms. I'm going to factor out x squared, which leaves me with x plus 2. And then over here, I'm going to factor out a -4, which also leaves me with x plus 2. That's very important. In order for factoring by grouping to work, these 2 factors have to be the same, all right? And the reason they have to be the same is because in the next step, I'm going to treat that factor as the GCF, and I'm going to pull it all the way out front. So when I pull it all the way out front, my other factor is x squared minus 4. So the partly factored version of this polynomial is x plus 2 times x squared minus 4. If I wanted to completely factor it, I would go on and factor this as x plus 2, x minus 2. But all we're trying to do is find zeros. So that's easy enough to do from this point. Since x plus 2 times x squared minus 4 is equal to 0, that must mean that one of these factors, either x plus 2 or x squared minus 4, is equal to 0. If x plus 2 is 0, of course that means x is -2. And if x squared minus 4 is 0, that means x squared is 4. And that means x is either the positive or negative square root of 4, which means x is either plus or minus 2. So the zeros of this polynomial are -2 and 2. The graph of f, which you'll see in a second, shows that each 0 is an x-intercept. And notice that the graph touches the x-axis at the point -2, 0, but it crosses right through the point 2, 0. So I love this example for that reason, because that kind of leads into the very next thing we're going to talk about, which is when can you tell whether the graph is just going to touch its x-intercept or cross right through it. And that has to do with a concept called multiplicity. I just love that word. What a great word. Multiplicity and x-intercepts. So here's another thing that sounds very complicated, but is really very simple. In factoring the equation for the polynomial function f, if the same factor x minus r occurs k times, but not k plus 1 times, we call r, the number r, a 0 with multiplicity k. So, you know what? This might be a good time to go back to the tablet. Okay, very, very simple concept. Suppose that f of x was x minus 5 to the power 4 times x plus 1/2. So multiplicity is really just the exponent that appears on the corresponding factor, all right? So if I were to set this thing equal to 0, hopefully it's clear to you that the solutions would be 5 and -1/2. Okay, those are the numbers that would make this function equal 0. And the multiplicities are 4 and 1. So it's just the exponent that appears on that factor. Of course, there's an invisible 1 right there. So that's the idea of multiplicity. I think I've kind of stolen some of the thunder from my, oh dear, next example. What are we doing here? New share, that's what I want. Okay, but that's fine, then I can leave that next example to you. All right, so it turns out if R is a 0 of even multiplicity, like it was in my little example, I had x minus 5 to the power 4. So 5 is a 0 of even multiplicity because the exponent on that factor was 4. Then the graph touches the x-axis and turns around at that point. On the other hand, if R is a 0 of odd multiplicity, like the -1/2 was, that factor appeared to the power 1, then the graph crosses the x-axis at the number R. Regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near zeros with multiplicity greater than 1. So that's something we'll try to keep in mind when we're drawing our graphs. And I'll point that out to you on any example that I notice at all. Oh my goodness, this is kind of similar. I probably had this example stuck in my subconscious. Anyway, they want us to find the zeros of the function f of x equals -4 times x plus 1/2 squared. I said plus, didn't I? -4 times x plus 1/2 squared times x minus 5 cubed. Find the zeros and give the multiplicity of each 0, and then state whether the graph crosses the x-axis or touches the x-axis and turns around, or I like to say bounces. All right, so take a second and think about that. And let's see. Okay. Oops. Okay, so we find the zeros of f by setting f of x equal to 0. If -4 times x plus 1/2 squared times x minus 5 cubed is equal to 0, that must mean that either x plus 1/2 squared is 0, which means x is -1/2, or it means x minus 5 cubed is 0, which means x equals 5. X equals -1/2 is a 0 of multiplicity 2. X equals 5 is a 0 of multiplicity 3. So here's the graph of that function. Since -1/2 is a 0 of even multiplicity, the graph is going to bounce at that point. And since x equals 5 is a 0 with odd multiplicity, the graph is going to cross right through that point. Notice, especially, you can really see it here, the graph flattens out a lot near x equals 5. All right, the larger the exponent, the more flat that graph will be near that x-intercept. All right, that brings us to the intermediate value theorem. This is yet another thing. Sounds very complicated. Once you see a picture, it makes perfect sense. So it says, if f is a polynomial function with real coefficients, and f of a and f of b, so a and b are some numbers, have opposite signs. All right, now before I continue, remember that f of a and f of b are y values, okay? So if that's true, if f of a and f of b have opposite signs, then there has to be at least one real number c between a and b for which f of c equals 0. Equivalently, the equation f of x equals 0 has at least one real root between a and b. Okay, so that's a lot to take in. So we'll do this example, and then I'm going to show you a picture that will make perfect sense. So in this example, they want us to show that the polynomial function f of x equals 3x cubed minus 10x plus 9 has a real 0 between -3 and -2. Okay. So it's helpful that they're giving me these two numbers, -3 and -2. What I'm going to do with those is I'm going to evaluate the function at those values. And if f of -3 and f of -2 have opposite signs, then we're done. That means, by the intermediate value theorem, that there has to be at least one real 0 between -3 and -2. So it turns out that f of -3, if you replace all the x's with -3, comes out to -42, which of course is negative. And f of -2 comes out to 5, which of course is positive. So that means by the intermediate value theorem, this function has at least one real 0 between -3 and -2. And here's the picture. So f of -3 equals -42 means the graph passes through the point -3, -42. And f of -2 equals 5 means the graph passes through the point -2, 5. So of course, in order to get from point A to point B, the graph has no choice but to cross over the x-axis. It can't just jump right over it like a piecewise function because, remember, polynomial functions are continuous. Okay, you can draw them without picking up your pencil. So that's the idea behind the intermediate value theorem. It's a very simple concept, but it's just an unfortunate thing with math. In order to use the proper notation and everything, it makes everything seem more complicated. All right, let's talk about turning points. In general, if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. So let me put a specific number in here and see if I can convince you of this. Suppose n was 6. The fact that f is degree 6 means that the most number of x-intercepts that this graph has is 6. All right, that would be if it factored into 6 different factors, each with an exponent of 1. So if the graph had 6 x-intercepts, then in order to get from one x-intercept to the next, one time maybe it'll go up, the next time maybe it'll go down, and then maybe go down again and then go up, I don't know. But anyway, in order to get back to the x-axis, the graph has to turn around. And so if your polynomial had degree 6, then the most number of turning points you could possibly have is 5, right? And you might have less depending on a couple of different factors that we don't have to get into right now. But that's the most number it could have. So now we're ready to talk about a strategy for graphing polynomial functions. So the first thing you can do is use the leading coefficient test to determine the graph's end behavior. Remember this thing. And then find your x-intercepts by setting f of x equal to 0 and solving the resulting equation. And then this is where you can use your multiplicity to figure out whether the graph is going to bounce at each of those x-intercepts or cross through. In number 3, you can find the y-intercept by computing f of 0. Remember, to find a y-intercept, you always set x equal to 0. It's helpful if there is symmetry. Basically eliminates half of your work, all right? If your graph has any kind of symmetry, then once you know what the right side looks like, you know what the left side looks like. So that's kind of a nice shortcut. And then finally, use the fact that the maximum number of turning points of the graph is n minus 1, where n is the degree of the polynomial function, to check whether it's drawn correctly. So let's use this strategy to graph the function f of x equals 2 times x plus 2 squared times x minus 3. So first, we're going to determine our end behavior. Now, when the function is written in this form, all factored out, it makes it just a little harder to see the leading term and the leading coefficient and the degree and stuff. So I want you to think for a second about what is the degree of this polynomial. All right, if you were to multiply this thing all out and then write the terms in descending order of powers, what would the first term be? Think about that for a second. Whenever I'm standing in front of a face-to-face class, I always ask that question, and sometimes it takes a minute or two to get an answer. All right, so I'm about to tell you. If you're not ready to hear the answer yet, just hit pause. All right, well, if you were to multiply this thing out, I'm going to put a, oh, you're kidding me. I was going to put a text box. Just a second. This has never happened before. I went to put the text box, and whoop, here we go. Okay, let me put my mouse back on for a second. Okay, I wonder if I'd have any better luck with the pen. All right, I'm gonna try it. It's not gonna be pretty. If you were to multiply this thing all out, the highest degree term that would come out of the x plus 2 squared would be x squared. And of course, x minus 3, you've kind of already got the whole story there. So when you were multiplying x plus 2 squared times x minus 3, the highest degree term that would come out of that product would be x cubed. And then probably the last thing you would do would be to distribute the 2. So the leading term of this polynomial would be 2x cubed. And then there would be some other stuff that I really don't care about right now. So I'm just going to put dot, dot, dot. All I really needed to know right now is that the degree of this polynomial is odd and the leading coefficient is positive, which means that the end behavior is like this, isn't it? Okay. All right, so let's see how I said that in here. So we've identified the sign of the leading coefficient and the degree, and that means the graph will rise on the right and fall on the left, just like you see in this little diagram here. Okay, so we'll keep that in mind as we move on to step 2. Step 2 is to find the x-intercepts, which are the zeros of the function, by setting f of x equal to 0. Now I like that the function is written in this form. It makes it very easy to solve that equation, which I didn't do here, so I guess I should switch over to the tablet. I'm kind of surprised I don't have that there. Okay, so let me go back to my tablet, which has fallen asleep. I hope you haven't. All right. Let's see. Yeah, I don't normally like these videos to be this long, but sometimes there's just a lot of stuff to talk about. Where is my mouse? Okay, there we go. We're almost done. As soon as we get through this example, we will be finished. Okay, I think I just gave away my password to get into my iPad, but that probably doesn't matter. Okay, what was this function again? I think it was f of x equals 2 times x plus 2 squared times x minus 3. Okay, so if I set that equal to 0, the only way that thing could equal 0, of course 2 can't equal 0. The only factors in here that could equal 0 are x plus 2 squared or x minus 3. If x plus 2 squared is 0, that means x plus 2 is 0. And if x plus 2 is 0, that means x is negative 2. If x minus 3 is 0, that means x is 3. So this graph has two x-intercepts. It has an x-intercept at negative 2. And while we're here, why don't we talk about the multiplicity? That came from the factor x plus 2 squared. So that's even multiplicity, which means it's going to bounce at the point negative 2, 0. And the x equals 3 came from an odd multiplicity factor. So it is going to cross at that x-intercept. All right, so I think we've gone ahead. Actually, I think this is all included in step 2. I was hoping maybe we had worked ahead a little bit. Okay, I might have to come back to the tablet. Let's see. Find the y-intercept by computing f of 0. Okay, so that I think we can do in our heads. So if we substitute 0 for both of these x's, this is going to be a 2 squared, which is 4. This is going to be a negative 3. So we have 2 times 4 times negative 3. 2 times 4 is 8. 8 times negative 3 is negative 24. So the y-intercept of this graph is 0, negative 24, which means this scale that I have set up here is probably no good. It only goes up to 12. I think this was the best grid that I could find. When I actually draw the graph, you'll see I use a different one. Okay, to help us determine how to scale the graph, we're going to evaluate f of x at x equals 1 and x equals 2. And the reason that I'm choosing those values is because they are between the two x-intercepts. Did I do that on here? No, I did not. All right, so let's switch back to the tablet. It's probably been about a year since I've looked at this PowerPoint, so I couldn't remember whether I had all this stuff in here already or not. I even looked at it ahead of time and I didn't notice that I didn't have it. All right, 2 times x plus 2 squared times x minus 3. So notice I've left blanks where the x's go. So when I replace those with 1s, what I get is 2 times 3 squared times negative 2, which comes out to 2 times 9 is 18, times negative 2 is 36. So this graph goes through the point 1 comma negative 36. And I said I was going to put 2 in here. Okay, so 2 plus 2 squared times 2 minus 3. That comes out to 2 times 4 squared is 16. 2 times 16 is 32. 32 times negative 1 is negative 32. So here are the points that I know so far on this graph. I know that negative 2, 0 is an x-intercept. I know that 3, 0 is an x-intercept. I know that 0, negative 24 is the y-intercept. And now I know about these 2 points. So I better make my scale so that all of those y values are included. And I will. All right, next, almost done. We're going to use possible symmetry to help draw the graph. So, oops, spoiler. Okay. I know that symmetry was a concept that a few people struggled with in chapter 1. So one last time, I am going to go over to the tablet and we will talk just one last time about how to check for symmetry. Okay. So symmetry is all about f at opposite x. So the original f of x is 2 times x plus 2 squared times x minus 3. So now I'm going to write the function like this, f of blank equals 2 blank plus 2 squared blank minus 3. And if I fill in the blank with an opposite x, let me now see if I can turn that into either f of x, in which case the function is even, or negative f of x, in which case the function is odd. Well, I think it turns out that this function is neither one of those things because, let's see, what do we have? You could write this negative x plus 2 as negative 1 times x minus 2. And you could write this negative x minus 3 as negative 1 times x plus 3. Now, when I square this factor, that negative 1 is going to disappear because the square of negative 1 is 1. And if I put these two together, I'm going to end up with negative 2 times x minus 2 squared times x plus 3, which is clearly not the same thing as the original function. I'm using some lazy notation here coming in a second. I hope you'll forgive me. So this function is not even, and it's also not equal to the opposite of f of x. Opposite f of x would just be, looking back up here, if I stuck a negative sign right here. I'm going to put a negative sign there and then I'm going to quick get rid of it. If this thing had come out like this, then that would be opposite of f of x. But that's not what I have. So this function is not odd either. So it's not going to have any kind of symmetry that we've talked about. Well, that's too bad. If it did, it would have just saved us a little bit of work. But actually, we're done with the work, I think, just about. So let's go back here. Okay, so using the fact that the maximum number of turning points is n minus 1, because this polynomial has degree 3, that means the maximum possible number of turning points is 2. If I drew my graph and it had any more than 2 turning points, that means something's wrong. So I've gone ahead and shown you the graph here. This is what it looks like. Notice that it's bouncing off the x-axis at negative 2, 0. It's crossing through the x-axis at 3, 0. It's going through the y-intercept of 0, negative 24. And it's also passing through the points, what were they, negative 1, negative 36, and 2, negative 36. All right. So that right there is a typical degree 3 polynomial graph. And I believe finally we have reach the end of section 2.3. So thank you for hanging in there, and we will see you next time.